This is our final section. This is difficult, and there's a lot of mathematics, technical underpinnings behind everything that we're going to talk about, which we don't necessarily have time to cover. So we're going to get the quick and dirty version of climate as a matter of risk, right, and decision-making. How do you approach decision-making and risk in the face of something like climate, which is terribly complicated and impactful? That's what this section is about. There's one small part at the end where we have the question of, okay, what should you do, which I try to avoid because it's really not the job of science to tell people what they should do, to answer questions about what is right or wrong, and trying to apply the tools of science to those questions of what is right or wrong, or what people should or should not do, has yielded some horrible results historically. So we try to avoid it as much as possible. We cover it a little bit at the end. This section is just sort of special. So this is Umberto Eco. He's an Italian writer. We'll just leave it at that. Futurist, essayist. He has a library, right, with something like 30,000 books in it. And there's kind of two kinds of people, right, who come in and see the library, right? There's the first kind who say, wow, well, but have you read all of them? And then there's the second kind who kind of understands that that's not really the point of having a library, right? Having a library is about having a collection in some ways of all of the things that you don't know. In other words, it's more of an anti-library, right? Instead of being a collection of books that you've all read and know everything in them, instead you have this collection of things that you know that you don't know, and then whenever you need to, conduct research, you're running into a problem or whatever, you go in and find what you need to find, right? There is a lot of debate about this issue of climate, right? Typically, debate on this falls into very tribal lines, right? People figure out what sort of cultural tribe they belong to, and then they figure out what that tribe thinks about the issue, and they say, okay, that's what I believe. That's what usually happens, right? In the world of people who are technically literate and scientifically literate, like the non-tribal world discussing it, you run into a different issue, which is that debates around climate change, discussion around climate change tends to fall along the lines of, okay, which computer models are better than the other computer models, and what specific things are we forecasting and what specific things are we predicting, and, whose model is better. And really, my claim here is that we can avoid that discussion as well. How? By admitting to how much we don't know about the thing, right? You can do the smartest thing in the whole world, which is to admit that the amount that you don't know about whatever the thing is just way bigger than what you do know, right? And something that is complicated, important, and how much you understand about it is a fraction of how much you could understand, and the thing is infinitely complicated to begin with. So what? So instead of necessarily looking at predictions and predictions about the future, instead, we should ask the question, what if there were no models, right? What if, not saying that these are wrong or useless, but just setting them aside for now, okay, what if we didn't have any reliable models? What would we do, right? And I would encourage you to even sit and think about that. At least for me, when I first kind of asked myself this question, I realized that this is actually a lot scarier, right? What if you admitted that you didn't know what was going to happen in the future and that the universe of possibilities was really big? That's actually even more terrifying in a lot of ways than looking at doomsday projections, and in a way that is ultimately productive. So this is well demonstrated psychological effect, replicated, empirically supported, right? If you have people who are gambling on stuff, and you take those people and you give them forecasts and projections and predictions about the future, no matter how nonsensical on one hand or how damning those projections and predictions about the future are, it actually ends up making the person feel safer and makes them take greater risks than they would if they had no forecasts or predictions or projections at all, right? So in some ways, as disastrous as these scenarios can look, right? So this is RCP 8.5, where we have 8.5 C of warming. Catastrophic, right? So Paris Climate Agreement is trying to limit it to like this scenario here, right? 1.5 to 2. There's others which are, business as usual paths, and, this is the we're wrong path. Okay. The better question really is to ask yourself, what if you didn't have those models and you had to approach climate as a question? What would be the right way to approach it if you just admitted that you didn't know what was going to happen? And here's my answer, right? So the first sort of fact from a decision-making standpoint that radically shapes the whole rest of the discussion, and has to, is that you only get one Earth, right? So the consequences of messing with it in some way, especially if that's done in a way that is irreversible or has cascading consequences, is really big, all right? The fact that there is one Earth, everybody has to live on it, radically constrains the kinds of risks that you can take, right? Because you only get one planet. So we'll start with that one. There's some other concepts that we need to build in the meantime. Okay, so some things fall into this world that I call mediocre stan, right? Things like height and weight. So if you took 1,000 people and you lined them up in a football field and you started tallying down their height and weight, after you had accumulated, 1,000 or maybe 10,000 of those people, you would have an extremely good idea of the average height and weight of, a person, right? And even if you were to add an outlier to that sample, right? A person who is the tallest, heaviest person ever, they don't change the average by very much. In fact, they're kind of diluted in a sample that big. They don't really change what just happened. On the other hand, if you take 1,000 people and you start looking at their net worth, right, amount of wealth they've accumulated, right, and you start to build up like a sort of average, right, of the average net worth of those people, all right, and then you add Elon Musk, whose net worth is $200 billion. Does that change the average? Yes. So wealth is going to be an example of one of those things that is dominated by extremes, right? You could have an extreme event which not only slightly changes the average, slightly changes the situation, but because of the extreme, event, it is the situation. Like, the net worth of, those 1,000 people now is his net worth divided by 1,000, basically, right? And same thing is true if you have, 10,000 people, right? The effect is going to be the same. Dominated by extremes and by outliers, right? And as a consequence of this, right, if I tell you that two people have a combined height of 12 feet, right, it's most likely that one of them is 6 feet tall and the other is 6 feet tall. If I tell you that two people have a combined net worth of $36 million, what is most likely is that one of those people is worth $36 million and the other one is worth 0. Why? Dominated by extremes. We can see this in graphical form, right? So this might be, height and weight, or you can think about this as calories, or you can think about this as any number of things that are constrained by physics. And this might be, I don't know, deaths due to disease, right? So you got nothing, 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 nothing. And then the Black Plague, right? And then, nothing, right? Small things. Or you can think about this as deaths in terms of war, right? So you have, post-Napoleonic era, right? Nothing, 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 quiet period, lots of tension that doesn't turn into anything. And then you get World War II with extreme event that dominates the entire thing, right? Just in graphical form. Okay, there's also this question of individual and systemic risk, right? So individual risk might be things like car accidents. They don't spread from one person to another. If you woke up tomorrow morning and you saw in the news that 1 billion people had died, they didn't die of car wrecks because this doesn't spread. On the other hand, if, you woke up and you saw that 1 billion people had died and you thought, oh, it's some strain of Ebola, that is possible because this is a systemic risk, right? Infectious disease falls into this category of systemic risk. It spreads, it can infect the entire population. So when you put these two things together, right, dominated by extremes and systemic risk, right, it spreads from one person to another and affects everybody, then you get this category of problems that simply cannot be accepted, right? You run into this category of risk that simply cannot be taken. Another example here, right? So these people are, highly sophisticated, I don't know, finance people, right? Who think that they're doing these really complicated things, but are actually just gambling, right? And whenever they hit the bottom, they go broke, right? And they stay broke forever because that's how it works. This is an absorbing barrier. It's, the financial equivalent of death. It's a state that once you enter it, you never come back, right? I'll maybe pause it here, but you can think to yourself, what is going to happen eventually as time goes on? The answer is that all of these people are going to go bankrupt, right? Because they're really just flipping coins, even if they think that they're not, right? They are playing Russian roulette. So here, where we have an absorbing barrier, right, something like extinction or death or total bankruptcy that cannot be recovered from, right, it changes the way that the game has to be played, essentially, right? You can no longer take risks that have any chance whatsoever of putting you down into the absorbing barrier, right? It's like, why does half the value of your car lie in the safety features? Well, because if you reach this state, then you never come back from it. And so it is worth doing everything possible to avoid ruin, right? To avoid hitting the absorbing barrier. It is also why traditional cost-benefit analysis, right, that you might learn in, a finance class, doesn't work for some types of problems. Like it doesn't work for Russian roulette. Why? Because you essentially are dividing by negative infinity, which is how much you lose if you hit the absorbing barrier. That's why you can't do it that way. Things which have high connectivity, like what? Like the ocean, like modern systems of transportation, modern human networks, are more prone to extreme events for reasons which are technical and mathematical and we don't really need to get into. It is why, over geologic time, oceans have been much more prone to mass extinctions than terrestrial ecosystems. The ocean systems are highly interconnected. The terrestrial systems are not. And so, because the ocean is so interconnected, it's prone to extreme events like mass extinctions, right? High connectivity also, in the case of human networks, make them more vulnerable to things like infectious disease, right? Once that network connectivity threshold is passed, all of a sudden you sort of cross the domain into everybody on Earth being able to get some sort of disease, right? So this is an extinction risk. This is a risk that cannot be taken. Why? It is systemic, it is prone to extreme events, and it could put everybody into the absorbing barrier. That's the idea. So things like climate change, infectious disease fall into this quadrant, right? Where you have extreme payoffs, right? So systemic risk, right? And dominated by extreme events at the same time. For all of the things that lie into this quadrant, you cannot take the risk. At this point, right? The burden of proof is not on the climate scientist to show that this is possible. Burden of proof is on everybody else who is skeptical of climate science to show that it's safe. In other words, we're in this situation where if there is any uncertainty as to whether or not emissions are unsafe, then we need to not do it. The same way that, back 50 years ago, right, when it was uncertain as to whether smoking really caused cancer or not, you still had enough information at your disposal to realize that you should not do it. Right? At that point, the burden of proof needed to be on the cigarette manufacturers to show that it was safe, not on people to show that it caused cancer. Likewise with climate, right? Burden of proof is on folks to show that CO2 emissions are okay, not the other way around, given the nature of the problem and given that the extent of harm has been demonstrated to basically be unlimited. So burden of proof lies on the skeptics. Here. This kind of summarizes this. I'll put a pause point there. As far as climate and you, what you can do things where you pay the costs and other people get possible benefits. Like what? Start a business, run for office, become an activist. Something where you take on the costs for yourself and you do need to pay actual costs, but other people might get the benefits as a result. What should you not do? Engage in rent-seeking behavior. And that last bit is the limit of the section on what you should be doing. Big questions. How does greenhouse effect work down to the last detail? The mechanics are important. Which gases are contributing? Where are they coming from? Which gases are they? What are the different characteristics between them? Consequences of climate change on the environment. How the climate has changed over deep time, at least in a broader sense, not necessarily to all the details. Consequences of climate change on human beings and how that can cascade into other effects. And that's it. Thank you.